Good evening, welcome to the first video on our special relativity topic. I'm actually going to do these ones a little bit differently. I'm not going to go through the same learning intentions that we cover in class. You can get those from class, and if you do miss one, please let me know and I'll provide you with a copy of the notes to look at yourself. However, what I do want to do is talk about each of the topics that we cover, or at least the subset of the topics, in kind of a more organic way. And what I'll be doing is unpacking one or two of the syllabus objectives on the topic. So under special relativity there is a set of topics that you can find on the eLearn site. I'm going to do two of them. I'm not actually going to go in order though. So the first one is about a non-Newtonian mechanic, such as the presence of muons, or non-Newtonian phenomena, such as the presence of muons, and I'll come back to those in a later video, because I think really you need to understand something a bit later on with time dilation and length contraction before we can really explain that. Otherwise you're just sort of going, oh yeah, this is the thing I'm parroting back. So in this one I'm going to look at these two points because I think they tie together quite well. The first is define the terms frame of reference and inertial frame of reference. So we need to be able to say what these two terms mean. And the second is recall the two postulates of special relativity. So let's have a look at some of the jargon here. Define in this case means that we need to be able to state what it means. To me, really you need to understand what it means so that you can use it in some of your work. So we'll need to go through those two terms. Recall in this case would probably be sort of an identify or just a state type question where you need to say, well, this is what they are. Some of the second postulate will be quite important for exploring the paradoxes a little bit later on, but otherwise it should just be a remembrance type thing. So recall the two postulates of special relativity. Well, the word postulate in this case means an assumption, so it's something that we're assuming to be true and then seeing what happens from it. Generally, some areas of physics and mathematics require this, where we need to assume that, oh yeah, this is true, and then we see what happens, and if we don't get any contradictions we tend to go, oh well, this kind of looks like it's true, or if it makes some good predictions that then are shown true, then we can go, well, these postulates are probably okay. The book does mention this, but it doesn't talk about the proof at all, but it does say that the second postulate is kind of redundant. We only really need the first, but the syllabus wants you to know two, so we're just going to stick to that. We're not going to worry about, well, this is why you don't need the second. No, we'll just stick with the two. So let's talk about those terms, frame of reference and well, what is a frame of reference? Because if we know what a frame of reference is, then we can come back to the inertial frame of reference. Right now, you are sitting here watching this video, or perhaps just listening to it and watching whatever, and there is a set of things that is some equal distance away from you, and there is a set of things that is some further distance away from you, and you are in the centre of your sphere of sight. Now there might be some walls in the way to stop you seeing what's behind them. If you stand outside, eventually you'll see the horizon, which is the distance that our eyes can see, but you are essentially the centre of your own universe. Don't let it get to your head. However, everybody else is also the centre of their own universe, and if you have a position, you can say, or you can interpret the world around us that, you know, maybe you see a dog, let's see if I can draw a dog, body, couple of legs, head, and a tail, and you might see that dog bolt past. Now, the thing is though, if that dog has moved from point A to point B, yeah, you can say, well, in your frame of reference, you were still and this dog just moved past, but it's also equally true for this dog to say that it was still, and it moved everything past it. Okay, and that's a fairly important idea because we're going to need it for our postulates a little later on. But these frames of reference, it doesn't actually matter which one you take. Sometimes a frame of reference might be stationary, like me sitting here in my chair right now. Sometimes a frame of reference might be moving. For example, I can currently hear my wife walking to the kitchen to get a drink. I can hear my bird jumping around in its cage having a squeak right now. All these frames of reference are equally true. So a frame of reference is kind of like, well, who is the center of this set of observations here? Who's this person in the middle? So if we think about frames of reference, then we've got things that are, they could be still, they could be constant movement. Perhaps you're sitting on a train, and here's a really great exercise. If you can catch one of the express trains from Darra Station shortly after an all-stops train has left a few minutes earlier, those two trains will catch up. And if you're sitting on the side of the train where you can look right out the window and there's the train itself, and you kind of just relax a little bit, you get to this point where now you're going, well, I'm not moving because you're not seeing any movement. You and this train next to you might be paralleling, and then suddenly you start to see it go backwards, and like, well, what's going on here? It looks like it's moving backwards, and something weird's happening, and often it'll jerk you awake. However, what's happening is that train is slowing down, and when we talk about relative motion, this will sort of tie into these ideas of frames of reference. So another good example, if you're on perhaps a bus, and you're not actually paying attention, you don't know if you're moving or you're not. Perhaps next time you're in the car and you're on a long straight drive, close your eyes and just try to relax and just see if you can actually realize that you are moving. If it wasn't the fact that you know that you're moving, see if you can try to realize whether or not you're moving. So we've got this still with this constant, and the last one is accelerating. So a frame will always be one of these things. You might be still, you might be moving, perhaps you're listening to my voice on your phone while you have a walk and you're walking at a constant speed, or perhaps you're accelerating. Maybe you're realizing you're late for school, so you're running down the street, or perhaps you're in a car going around a corner. All these things are accelerating. Now, there are certainly rates of change of acceleration, but we don't need to care about that because this is the cut-off point. These two things are what we call inertial reference frames, while this is a non-inertial. So I'm going to actually do this live. So I'm loading up a Google site right now, and I'm going to look up what is the word inertial. So if we do a definition for inertial, just gives us a definition in relation to those words. So what does inertial frame of reference mean? See, it's coming back to this definition, but it is not really explaining why. Okay. So it's not really explaining why it's using the word inertial frame of reference. It will have something to do with the word inertia in this case, the tendency in an object to keep moving in a constant line of velocity. Remember back to Newton's first law. However, it's something that in this case we need to definitely know the definition. What's a lot easier to think about is this idea of why is there a difference. So let's start off with just calling them A type and B type. Okay, or type 1 and type 2 frames. Let's imagine a type 1 frame. Let's imagine an inertial frame. Perhaps we're in the lab. Here's our lab bench, and we've got a pendulum. And it's swinging backwards and forwards. Now it will swing at some particular period. It will oscillate backwards and forwards with a certain time, and it will depend on the length, and it will depend on gravity. So its period will be equal to 2 pi square root L over G. It won't matter how far we pull the angle, at least as long as it's reasonably small. Length and gravity will be all that matters. So that should be a square root for the whole thing. My writing's atrocious. Now, if I'm moving at a constant velocity, as in I'm not accelerating this, well, they're going to be the same thing. It wouldn't be able to tell the difference. They actually did some tests on this back in the I'm going to say late 1800s, early 1900s, when they were trying to determine if there was a way to work out if you were moving, at constant speed in a without being able to observe the outside, which is kind of important because we'll talk about that idea of relative motion a little bit later on. And so if you conduct this experiment on a train that is going at constant speed, so it's not accelerating, it's not jostling around, it's just moving at a steady speed, you will get the same number. If you've ever, actually a good way to think about this is imagine that you're walking on a train and it is not accelerating, it's not going around a corner, it's reasonably smooth track, it's quite easy to walk down it. You might go, well, what does this have to do with conducting an experiment? The thing is, your everyday notion of the laws of motion, cute or rhyme, I guess, or your everyday perception of these laws depend on things always being the same. So if you've ever been on a boat, your body acclimates to this new environment. You get off the boat, you keep trying to bob and weave, and you stumble around like you're a little drunkard for about 20 to 30 minutes until your brain reacclimates to the fact that the ground is not moving, or is not constantly accelerating up and down. Sailors have this massive problem, especially in the olden days when they were at sea for many, many years at a time, where they would just bob and weave when they got to shore, and so they kind of look like they're drunk stumbling around. However, let's take this same experiment now and let's think about a system that is constantly accelerating. And perhaps it's accelerating this way, mostly because that's going to be easy for me to draw. If it is accelerating this way, well, our string is no longer going to hang straight down, it's going to hang this way. And if we think about what's happening here, the system is being accelerated. Inertia will want it to stay behind. It wants it to stay in the position it's used to. It will want to keep doing what it's already doing. And so, our ball ends up hanging backwards. Now, this means then we have some acceleration this way on the ball. There'd be some acceleration this way, and there would be some acceleration this way. What then would that do to my period? Would it have an effect? Quite probably yes. So t might still be equal to 2 pi root L over g, but there may be some other constant somewhere. In fact, there probably would be. The period would have changed. As such, because here's the thing, as I'm moving in and out this way, that will change, but this will still be acting with the same amount in the same direction. So the period will change here. So this is what we mean by inertial versus non-inertial, and what it needs to come down for you is that you remember that whether or not this means that the velocity is constant or there is no acceleration. Okay, so here v is some number, could be 0, could be not 0, but a is equal to 0. Here v doesn't matter, but a is not equal to 0. So that is our big thing about inertial versus non-inertial reference frames. Taking from this, then, we have to ask ourselves about what does this have to do with our postulates of special relativity? And the two postulates are, one, the laws of physics, are the same in all inertial reference frames. And I know that you probably can't read my handwriting here, but that's why I'm saying it out. So the laws of physics are the same in all inertial reference frames. It's also in your textbook, so go back to that if you need be. Secondly, and this one we haven't dealt with yet, but I'm going to do the video repeating the experiment we did just so you can see the math for yourself. The speed of light is the same in all reference frames. I'll actually double check that though. So if we think about what that actually means then, so the speed of light is this absolute value, 3 times 10 to the 8 for the syllabus. The actual number is 2.99, and then I think it's a 7 after that. And so we are not going to worry about to that precision because everything's been rounded off to kind of like 2 decimal points in our syllabus. So you just have to worry about 3 times 10 to the power of 8, 3.00 times 10 to the power of 8. That precision still exists. Now, if we look at the difference going on here, one is that, sorry, not in all reference frames, in all inertial reference frames. Okay, so that means if something's accelerating, the speed of light won't necessarily be the same. However, the first postulate is that everything is the same in all inertial, that is uniformly moving frames of reference. So you need to memorize these two. That's basically what it comes down to. The Earth, even though it's accelerating, the acceleration is considered to be small enough that it probably doesn't matter too much. And so we just pretend that we're on an inertial reference frame. It may be down the track that we have to get to a point where our requirement for our laws of physics needs to remove that error, because there would be some error being introduced by it. Some experiments would have it, some experiments might not. There should be ways of accounting for them, and so we would have to get rid of those errors, and maybe we'll see it in our lifetime, maybe we won't. Alright, so this video has only been focusing on these two things. One, define the terms frame of reference and inertial frames of reference, which we've done. Remember, a frame of reference is anything where we have uniform motion, whether that's standing still or moving at a constant speed, doesn't particularly matter, because effectively they're the same thing. You are your centre of your own personal universe, however, so is everybody else. And secondly, you need to recall the two postulates of special relativity. The next two videos we're going to focus on relative motion, and then the third video will be simultaneity, which is the stuff we covered in our first week of the unit. We will then start dealing with time dilation and length contraction. I will continue to try to provide good reference videos for you to watch on these topics, because it's important that you see it from as many different angles as possible. Alright, thanks for listening guys. Have a great evening and holiday.